explore how to realize the full potential of connected and automated vehicles. Dr. Xiaopeng Li is currently a professor at the Department of Civil and Environmental Engineering and an affiliate at the Department of Electrical and Computer Engineering. He has served as the director of one U.S. Department of Transportation National University Transportation Center, National Institute for Congestion Reduction, and has published over 100 peer-reviewed journal papers. He received a bachelor's degree in civil engineering from Tsinghua University and a PhD degree in civil engineering, along with a master's degree in applied mathematics from the University of Illinois at Urbana-Champaign. Please welcome Professor Xiaopeng Li.
Thank you, Kiki. Good afternoon, everyone. Thank you for tuning in. Today, I'm going to talk about an emerging area in the civil and environmental engineering, particularly in transportation engineering, that is connected and automated vehicles. We're going to talk about how to evaluate the existing technologies as well as developing new technologies in this talk. So, as you may know, in the existing transportation systems, there are many vehicles driving around, and these vehicles are all driven by human drivers as of today. So this is probably what you see and experience around and at UW-Madison. Whereas there is a new trend of technologies in this field of transportation that have a potential to revolutionize the human-driven vehicle-dominated traffic systems. So one technology is called automated vehicles. That is basically to replace human drivers with robot drivers. The vehicles can be controlled, or at least partially controlled, with computers and robot drivers. Another technology is so-called connected vehicles, which means the communications between vehicles and other vehicles and also other road users that share the rights of way. There have been quite high hopes on the benefits of the so-called connected and automated vehicles technologies. Regarding the safety, people hope to reduce over 90% of the crashes with these technologies. Regarding mobility, they hope that highway capacity could be multiplied, for example, to be tripled, quadrupled with these technologies. Regarding energy efficiency, there is a hope that these technologies could improve energy consumption efficiency, could save energy consumption by over 50%. What was exciting was that these technologies were tested and showcased to the public even in over 25 years ago. So this picture shows a platoon of vehicles that follow each other very closely with connected and automated vehicle technologies on California highways about 25 years ago. So this was very exciting, and the vision back then could be like this, so in a fun way. So all the road users could coexist harmoniously and pass the intersections and bottlenecks without any stopping due to the perfect automated and connected vehicle systems. Though I'll be a little bit scared walking across the intersection like this, but aside from the pedestrians and bicyclists, so the nice movements of the vehicles indicated what we hope our future transportation system could achieve. So in order to realize this vision, we have to go through some rigorous engineering processes. For example, we need to understand and evaluate the existing automated vehicle technologies that have been deployed in our traffic fleet. And also, on top of that, if we find limitations of existing technologies, we want to develop new technologies such as cooperative driving automation to improve what we have today going to the future. So I'm going to talk about the evaluation of existing production automated vehicles first. So actually, automated vehicles are no longer fictional or imaginary. There are a lot of vehicles today that are running everywhere in the world, have equipped with a low-level automated vehicle technologies, low-level automation, level 1 and level 2. So these technologies are called advanced driver assistance systems, or ADAS, and the longitudinal control, how to control vehicle longitudinally, is called adaptive cruise control. And basically, for vehicles that have adaptive cruise control, they could control their speed and acceleration based on the sensing information from the perceived spacing and also the relative speeds between the preceding vehicle and the subject vehicle. And if you have a vehicle like that, you're going to have control buttons like these on your vehicles. It's just like set speeds and adjust the spacing to follow the preceding vehicle. And by adjusting the spacing following the preceding vehicle, you can see different bars showing on your dashboard. And actually, these vehicles have grown at a very rapid rate from 2% in 2015 to a projected 40% in the year of 2040. And 92% of the new cars manufactured in the US have a trim with the so-called level 1 automation, that is longitudinal control. And over 50% of them have level 2 automation, meaning both longitudinal control and also the lane keeping, lane changing functions. So how to evaluate these existing technologies and to check whether or not they have fulfilled the promise, as I discussed earlier. So these technologies are in general like black box. You have to collect the data to measure their performances. So in order to collect the data, you can get to such vehicles from dealerships and rental companies, and you can also equip the vehicles with non-destructive sensors such as GPS, such as CAN bus readers, basically lots of sensors that can measure the vehicle's movements and trajectories. So with these data collected, you'll be able to plot out lots of information regarding the status and motions of the vehicles. For example, the speed and gap history over time, and the location trajectories of these vehicles. With such data, you'll be able to build analytical models to describe how vehicles move. For example, this is a simple model that shows how the acceleration of the following automated vehicle will change in response to the speeds of these two vehicles and the gap between these two vehicles. And with individual vehicle models, we will be able to construct complicated simulations to analyze a system at scale with many vehicles. We can build a simulation with simple settings, or we can really use the advanced 3D technologies to show very nice graphic user interface and visualize a simulated city. What's interesting is that today you might be noticed many AI and generative AI technology development. Some of these technologies have been incorporated in our field to generate transportation simulation scenarios, and some of these studies have been very visible and well accepted. For example, this study has been published in a well-known journal, Nature. And with these study efforts, you will have a relatively good understanding about the performance of the existing vehicles that have automated that have automation features and functions. For example, you can measure their safety, energy, mobility, and equity performance. And you may find that these performance aspects are not balanced as of now. Maybe one areas of the focus of today's industry, and the other areas have been left behind. So there will be limitations and things that we want to improve about the existing technologies. This leads to the next direction of research, that is to develop new technologies to improve what we have now, so-called cooperative driving automation. So what is the vision of cooperative driving automation? That is to coordinate vehicles, infrastructure, and control units to let them communicate and work together to improve the overall traffic performance at once. That includes safety, mobility, sustainability, as well as equity. This figure here gives you an example about what cooperative driving automation can do. So this is over time as the x-axis, and the y-axis represents highway segment that leads to a signalized intersection, and the signal alternates between green and red phases over time. And these curves that you can see show the trajectories or the motion paths of the cooperative driving automation vehicles. And you can platoon them together, and you can have them plan their trajectories very well to coordinate with the signal timing so that they can pass the signals intersections without any stopping. And this is going to achieve very well safety, mobility, sustainability, and equity performance. So in order to achieve this vision, we have to build new automated vehicle control logic and overall system management methods. For example, some of our study focus on replacing the existing reactive-based control, rule-based control with model predictive control and online learning paradigms. So the model predictive control basically means we can utilize not only the information observed in the past, but also the predicted information and communicate the information about the future. And online reinforcement learning takes the advantage of the adaptivity and the high predictability of these learning models and AI models that will improve the accuracy of the control as well as the adaptivity to varying environments, to complex real-world environments. So with that, we will be able to do some lab testing with small scale, reduced scale robot cars to achieve things like platooning formation and platooning splitting. And these can be done in a very affordable setting and for education and research purposes. But we're not satisfied with the toy scale demonstrations just for the proof of concept. We want to realize them in the full-scale real vehicles. So for that very reason, we assembled cooperative connected automated vehicles test bed that houses multiple connected automated vehicles. For example, some of the vehicles you see here are what we have developed in-house. And we also developed portable roadside devices, as you see here in this figure. We have communication units, computation units, as well as the traffic signals and sometimes variable message boards to set up portable environments for testing these vehicles. And these vehicles provide us a very one-of-its-kind platform to experiment on novel ideas. For example, this is a field experiment about longitudinal trajectory control coordinated with traffic signals. So here you see a CAV, connected automated vehicles, as highlighted in the red box. The other vehicles are human-driven vehicles. So there is a traffic light downstream that is red and will be turned to green. And so this CAV knows the signal timing of the downstream signal light. So it will drive smoothly to avoid stopping. You see, when the test starts, these human-driven vehicles will just get to the downstream signal and make a full stop, whereas this CAV will make some smart movement like this. It will just smooth its trajectory and catch up to the queue without stopping and passing the intersection at the right time. So finally, I want to wrap up my presentation by acknowledging my collaborators and major external sponsors. And I want to let you know that actually our test bed is already housed in the engineering center building, the auto workshop. You're welcome to visit us. And this is my contact. Again, thank all of you for tuning in. And please feel free to post your questions in the dialogue. And I'll be happy to answer any questions. Thank all of you again. Have a good rest of the day.
Thank you for watching this Badger Talks live event produced by the University of Wisconsin-Madison through UW Connect's outreach and the Office of State Relations. Follow us on Facebook and YouTube to see the library of past recorded talks. Please visit badgertalks.wisc.edu to see the schedule of upcoming talks, sign up for the Badger Talks email list, and search the roster of over 400 UW experts who are available to give talks on important issues in your Wisconsin community.